D, and C and a 1 you go to F. And are D and F distinguishable?
F to C. We're looking at,
Oh, sorry, F. We're doing A and F, so it's D and C. Are D and C distinguishable? No. So we have not now determined that A and F are distinguishable. As far as we know, they're still undistinguished. They still might be the same. However, if later on in this process we find out that D and C are distinguishable, then what should we do?
Go back and make AF.
Then we should go back and put an X in AF. In order to do that, here's how the algorithm actually works. You go into, let's do the 0 first. 0 ended us up in B and E. Go into the BE state right here and put in AF. And if we ever get an X in here, we're going to go back to AF and put an X in there too. We'll also put an AF in what pair of states? In C and D, where you go on a 1 from AF. So in CD, which is here, we'll put an AF. This means that later on, we're going to go through this row by row. Later on, as we hit these two states, if they end up having an X in them, we will backtrack and fill an X there. This backtracking can wind up. If there was some letters here, we'd backtrack further up. But this was the first one, so there's no backtracking. All right, let's continue. We're going to go through the whole set of empty squares, one at a time. And when we're all done, we'll have all the dependencies looked at, and we'll have a sense of whether these states are distinguished or not.
Checking single length one string.
Yes. Yes.
And that's enough? Or?
Yes. And it's not obvious it's enough, but it is enough. I'll try to explain why it works later. I think it's better for me to do how it works first. And it is going to be enough, because really what's going on, this is a single length information, but later on, if we find that these are distinguishable, and then we go back and make that distinguishable, that was distinguished thereby by a double symbol. So the amount of your backtracking is the size of the string that distinguishes it. So you can't have backtracking more than 1, 2, 3, 4, I guess 5 is the longest backtrack. So that's what you asked before. Let's go on. What about AD? What does that depend on? AD, what does it depend on? What does the distinguishing characteristic of AD depend on? It's distinguished if what other states are distinguished? AD is distinguished if BE is distinguished. So I'll put a dependency line here. This graph has nothing to do with a finite state machine directly. It's not a finite state machine. It's just representing these dependencies so everybody can see what's going on. AD depends on BE through 0, and AD depends on AD with 1. If you ever get something that depends on itself, you don't bother writing in AD to itself, because that's never going to happen. In fact, when you see this happening, as far as you're concerned, that part of it says that these two states are indistinguishable. As far as the 1 is concerned, they might as well be the same state. It depends on itself. It's never going to get distinguished. But it might get distinguished if B and E get distinguished. So let's go to BE and add AD in to that list. And now let's continue on with AC. What does AC depend on? It depends on BE again. And what else? AC. Oh, just BB. Whenever you get something like this, that means both states went to the same place. Those are automatically indistinguishable. So it certainly does not distinguish AC. These pairs never get X's on them. They're automatically empty. What else does it depend on? And DF. Where's DF? Here. So what goes here? AC. So we don't know if any of these will end up being distinguished. Right now, where they're not distinguished, it depends if one of these get distinguished later. And now we're just going to continue on to the second row and look at BE.
look ahead for a second. Where are you going after you take this?
When I'm done looking at all these empty squares, and I'm finished backtracking all the x's, then I'm finished. And at that point, I'm going to look to see how many x's I have. And based on what the x's are, I'm going to collapse this picture down to a simpler picture, making all the states that are indistinguishable from one another into a single state. There's really a lot of math behind this that I'm leaving out for a minute, but I'll just briefly mention that this is based really importantly on this idea of an equivalence relation. Deciding whether one state is distinguishable to another is an equivalence relation. And the reason that's important is that when I'm all done, I don't want to have A, C, and F equivalent to one another, and also have D, C, and F equivalent to another, but have A, D be different. That would be crazy, because then I couldn't collapse it. I'd have to collapse A, C, and F to one state, D, C, and F to another state, and somehow leave these independent. So when we're all done doing this, if you have any three that are all the same, and then some subset of them are the same with another one, then that one is the same as this one too. It's an equivalence relation. It's transitive. So you never get a problem with collapsing it, and you'll see that at the end. But your question about where we're going is important. When we're all done, we're going to collapse it down. And we can collapse it down because it's all an equivalence relation. All right, where are we up to now? BE? Okay, so who can do this? Who's not afraid to try? Depends on CF. Why? Because B on a 0 goes to F, and E on a 0 goes to C. Depends on CF. And what else does it depend on? Depends on itself. So we go to CF, and we write in BE. Now we're going to go down to this CF. If this gets an X, we're going to go back to here and put an X in. And we're going to go back here and here and put X's in. Right? We've got a lot to do if any of these get X's. If they don't get X's, then they're still indistinguishable. So let's go to CF and see what happens. Let's actually just leave it from here. CF, what does it depend on a 0? Depends on BE. What does it depend on a 1? You see this funny graph? It's not a finite state machine. It's a graph. It's a directed graph. It represents something. It's something really important. It represents the dependencies of the pairs of states on each other. The vertices in this graph are pairs of states. The edges are, there's an edge from here to here if this pair is distinguishable makes this pair distinguishable. So CF depends on BE. What does that mean? We're not going to go back here and put CF in this line, because that's a cycle. We never go back. We go forward and put things in, but we never go back. Going back means we found a cycle, and it means we're not ever going to get a distinguishable characteristic. So we leave that, and we move on to CD. What does CD depend on? BE, right? What else? Well, AF is back up farther up, so we're not going to put anything there. And BE is farther back, so we're not going to put anything there. So we move on. Still nothing distinguishable. Now we're going on to DF. DF. DF depends on a single E. That's indistinguishable. Don't get anything from that. And it depends on AC, which is further back up there. So we ended up finding nothing but all these cycles of dependency, none of whom were dependent on any of the things that had X's in them. So we hit this last one and it's done. We are done now with the algorithm. What this shows is that the only distinguishable states in this picture that we started with were the ones I started with. We didn't pick up any on the way. I'm going to do examples where we do pick up a lot along the way to show you that later. But this time we went through, we picked up nothing on the way. Let's finish it up and rewrite this picture.